Okay. So in the last class, discussing operation regions of transistor. Okay. So let me give you one question: how to find the operation region? Uh, now onwards, I will use only NK transistor. This is your transistor.
Sure.
Just 1 minute. Yes, tell me.
Sir, your voice is not clear.
Okay, is it okay now?
Yes, sir, perfect.
Thank you. So this is your 5-volt battery, and this is 200 ohm resistance, and put it what resistance also here, 3 kilo ohm resistance. Okay. So now for you have to find out that operation region of this transistor. So your beta is basically given as 100. Okay. So you require at least 2 biasing. If you want your transistor to work, you need 2 biasing. Means you want a biasing in the input and one is the output. Okay, because you want to apply the voltage at ammeter base junction. So like this is the base and ammeter are applying this one. Similarly, you want to apply the voltage at base collector junction. So this is the base junction, this is the collector junction. So directly if you are applying at collector and ammeter, directly this VC is equal to your VCE and VCB and VBE. So you have to apply voltage here. So you apply here, that meaning the same. So that means basically the meaning is that you have to apply 2 voltages. You need to use 2 batteries or 2 biasing for every transistor to work. Okay. Now the VB is given in the question. VB I have told you already. VB will be always 0.7 for this junction. Okay, voltage drop. This is your collector junction. This is your ammeter junction, and here the voltage drop will be VCE. Okay, and here current will come. So here IB current will flow. IB, okay, and here a IC current will flow, and IV current will go down because this is the NPN transistor. Yesterday we discussed NPN transistor. What happens? Okay, current comes out of the terminal. Okay, now this 5-volt battery. Okay, what is the operation reason for this given circuit? This values of voltages and resistances. Okay, so we need to find. Now in order to find the operation reason, okay, for common ammeter configuration, you always need to remember the graph what we discussed yesterday. That is your graph. This was your graph. Okay, so you have to find if it is the active region, your VCE need to be positive. Okay, because VC cannot be negative. Right? You apply positive battery, VC cannot be negative. So VC at most can be 0. The drop here may be 0. Okay, so VC should be positive. And I told you if you want to save place, you want to work them to active region, VCE should be greater than 0.7 volt. Okay, much greater than 0.7 volt. So it's 1 volt, 1.25 volt, or 3 volt, 5 volt. If you want your operating region to work in the middle of the active region, that time you should need at least 2-3 volt VC and a drop here. Okay, so VC should be positive. IC value should be greater than ICO. Okay, that means if your IC is only equal to your ICEO, that time you can confirm that IB 0 and the operation region will be, even though this is a positive, but operation region will come here somewhere here.
Okay.
That is cutoff region. Okay, those things you have to take care. Now there's a very simple method to find whether your operation region is active or cutoff or saturation. Okay, let us first calculate the IB value. IB value. So IB value. So the first thing is confirm EB junction is forward bias. That is the first requirement. So IB is not zero. Okay, you're applying some voltage, so obviously some IB will flow. So IB is not zero. That means your EB junction is forward bias. Now this is NP and transistor NP. That means here you are applying positive. So this junction should be reverse bias. So you're applying positive here, and automatically this is also reverse bias. So this is a forward reverse. So this should be active region, but you have to confirm the value, whether what is the value of VCE, whether it's coming near to saturation region or not. Okay, so of course now let us find out the value of IB. So IB is what? IB is your how to find IB. So you come in the input circuit. You have two circuits. This is the input circuit. This is your input circuit. Okay, and this is your output circuit. Okay, first loop. So input circuit, you can write -5. This is the IB into 200 ohm. Now it is 200 or 200 kilo ohm. Let me check. 200 ohm only is given. Okay, if with the change, we'll see later. 200 ohm only here. Okay, 200 ohm. And then you have been given this VB 0.7 volt equals to 0. Okay, so from here I can find IB equals to 5 minus 0.7 divided by 200, 4.3 divided by 200. Okay, tell me how much is coming. So this is how much is coming in milliampere. That means this should be in microampere. Okay, they should be to put it 1000. Okay, this should be 200 kilo ohm. 200 kilo ohm. So now tell me how much will come. 21.5
21.5 microamp.
21.5 microampere. Very good. 21.5 microamp. Okay. It's coming. If I put only 200, then how much will come? If I put only this one, then this will come. This will come that much, na? So this will be how much? 21.5 milliampere. This should be very high. Okay, microampere only. So let me check the values, whether I am putting some wrong values or not. Because IB will be always in milliampere only. So 4.3.
सर आई भी माइक्रो में आता है ना बेस
हाँ माइक्रो में आता है, पर मैं देखूँ इसमें इतना प्रॉब्लम क्यों हो रहा है. ठीक है, चलो ठीक है, करेक्ट. जो भी आएगा देखेंगे अभी. Now you want IC, you got IB. IC will be your beta IB. So beta is 100, and this is your 21.5 to 10 raised to power -6. Okay, how much will come? Tell me, how much will come? So this will be 21.5 into 10 raised to power -4. Okay, or you divide by 10 and divide by 10 here. So this is 2.15 milliampere. Okay, perfect. 2.15 milliampere. Now you have to find IC saturation. Okay, IC saturation means this circuit here. This is your VCC. So this is the input. Okay, now let me discuss the output equation. So output equation is minus VCC plus this IC. This resistance called RC, ICRC, and then the voltage drop VCE equals to 0. Okay, so my VCE will be equal to VCC minus ICRC. So always you have to write two equations for output and input. Now VCC is given 10, IC you know 2.15 milliampere, and RC is given 3 kilo ohm. 3 kilo ohm. So this cancels out. Okay, so you got 10 minus 2.15. How much is coming? Tell me. This will be 6.15145.
545
You saw 3.55. 2.55 volt. That means this is somewhere here. Okay, so obviously Now VC, you want to check whether it is a forward bias. This is a forward bias, perfectly forward bias. Next thing is you want to find what? You want to find VCB. So you have VCE is equal to VCB, this voltage, plus VB. Now VC is your 3.55. So from here you can find VCB. So 3.55 minus 0.7. How much is coming? Tell me. 2.85. 2.85 volt. So VCB is positive. And for NPN transistor, okay, for NPN transistor, this VCB should be positive. This N should be connected to plus. And if N is connected to plus, that means that is the reverse bias. This is already forward bias, and P is connected to plus, N is connected to plus. The voltage drop across N is, and this base is positive. So this itself shows that your biasing is perfect. I made 4 column na? So forward, reverse, forward biasing, and this reverse biasing itself confirms that this is the operation region is active. And here also you can see if the VC is much far than the 0.7 volt, then the operation region is active. Okay, so these are 2 methods, and one more simplest method is there by you can directly tell whether it is the operation region is saturation or cutoff. Now you find IC saturation. Okay, IC saturation means this, when VC is 0, the current corresponding to VC is 0. Where, so this is basically what? This is basically your line equation. Na? You want to find what is the operation region. Operation region means you want to find what is VCE value and IC value. So VC we find this is 3.55 and IC value is 2.15 milliampere. Somewhere point is here. Okay. Now in order to confirm reality this point is here. But there's one more test. You can calculate IC saturation. So IC saturation means you have to put VC equal to 0. VC equal to 0. If you put VC equal to 0, that means you will calculate IC saturation. You put VC 0 here, then your IC saturation will become VCC upon RC. Remember this formula. VC equal to VCC minus RC. If I put VC 0, always for saturation, I will do VC 0. This drop will I'll make 0. If this drop is 0, this become VCC upon RC. Now find the IC value of IC saturation. How much is coming? So if you put this value IC saturation, okay, VCC is your 10 volt, RC is 3 kilo ohm, that is 3.3 milliampere. 3.3 milliampere, and IC saturation is greater than actual IC what we calculated in the circuit. So whenever IC saturation is greater than IC, you can write the operation region is active. The transistor is working in the active region. Okay, so I told you 3 things, 3 ways to find. Okay, first you find only IC saturation. If IC saturation is greater than IC, it's a saturation. If IC saturation is less than IC, then the operation region is saturation. Operation region is saturation. Okay, so now this is active. This one thing confirm. Or second thing, you find the value of VC and you see what is the value of VC, whether it's coming cut off or this one. So this is coming here. IC is not 0. IC is very high, much higher than the reverse saturation current. Is not microampere. Okay, so somewhere here it is there. That means operation region is this is the active region. Okay, or the best thing is the best test is you find the VCB, because that is the definition. Na? The fundamental main where we are starting. We told that operation region is active and this is reverse bias and this forward bias. So I calculated this. This is the positive value, and this is VCB is also reverse bias. So VCB was positive. So you can do any test. Okay. So better, this is simplest. You calculate IC saturation or see the VCE value, and then that is the simplest thing to decide what is the region is operational or active. Okay. So let me do one more problem. So now we have decided the IC and VCE. So my operating point operating point for this circuit P is what? VCE was how much? 3.55 and IC is 2.15 milliampere volt. So this is my answer. This is my point P, operation leader. Now, any student has doubt? Tell me. Are you
Clear,
able?
sir.
Oh, clear? Na? Okay. So I'll give you one more question now. So this is very easy to find. If you know the apply KVL, some nodal analysis, you can easily find the voltages for every circuit. You can tell whether it is a working operation region is what. Okay. So now I'm giving one more question. .7 volt. This is 10 kilo ohm. This is 2 kilo ohm. 10 volt. Okay. So tell me, what is the operation point? 10 kilo ohm, 2 kilo ohm, 10.7, 10, and you can take VB value 0.7. Sometimes it is given 0. VB value is 0.7.
So beta.
Beta value is 100. Beta value is 100. So first we have to find the IB value, and here we want to find the IC value. And this is ammeter current IE. This is an NPN transistor, so currents are coming like this. If it's a PNP transistor, everything become opposite. So first you have to take this loop, and then you have to take this loop. Okay. So this is input loop. Okay, input loop because we are applying in IB is input current, minus 10.7 plus IB into, generally it is called RB. Okay, value is given 10 kilo ohm, and this VB is your 0.7 volt equals to 0. So IB will come 10.7 minus 0.7 upon 10 into 10 raised to power 3. That is 10 upon 10 into 10 raised to power minus 3. This is 1 milliampere. Okay, IB is 1 milliampere. And now you can find for the output loop. Output loop, you can put here minus this is VCC. Okay, so minus VCC plus this is given RC, IC, RC. Okay, plus the drop here VCE plus VCE equals to 0. Okay, now you want to find the value of before that the IC value will be how much? Beta IB. So beta is given 100. Beta is 100. So this become 100 milliampere. Okay. Now you find VCE. Okay. Now first of all, you have to check IC saturation because this is coming too much high. Okay. So let us find, before writing this equation, let me find the value of IC saturation. So IC saturation, tell me what is the value of IC saturation? What is the formula?
VCC upon RC.
VCC upon RC. 10 upon 2 kilo ohm. That is how much?
5.
5
Yeah.
milliampere. Okay.
Yes, sir.
So this is very less compared to IC saturation is less compared to IC. So automatically you can say that you are in IC saturation. You are in IC saturation. The operation is in saturation. But one thing you have to understand: the current cannot go beyond this one. Current cannot beyond go IC saturation. It cannot be more than IC saturation. Why? Because if you seen the graph, okay, if you seen the graph, the maximum possible value is IC saturation. Okay, if your value is coming more than this one IC saturation, that means your VC is negative, and VC negative cannot possible here. Okay, if I put this IC 100 milliampere in this equation, so VC will come negative. Check it. VC will come negative. Check it.
Yes,
And
sir.
VC
190 आ रहा है माइनस का.
कितना आ रहा है?
Minus 190.
Minus 190. Let me check.
Yes, sir.
190 आ रहा है या 19 आ रहा है?
Minus 196.
Minus 190 आ रहा है.
Okay, minus whatever. I'm not good at calculation. Please check it. Okay, it's coming minus 190 volt. That means
Yes.
somewhere here. This is not possible. Okay, here itself it's a saturation. So here is a more saturation, but it's not practical. Okay, so that means this is wrong. This the value is wrong. Okay, so at most you can take the value of IC saturation. Now put if you put IC saturation value, automatically VC becomes 0, because by keeping VC 0 only we got this IC saturation. Na? So that means the operation region is saturation. Operation region is saturation. Okay, and the operating point will be what? Tell me operating point. Where is the operating point? Operating point means value of VC. So for IC saturation, what is the value of VC? 0. So operating point will be 0 and 5 milliampere. This is your operating point P. This become point now. If you take this value of IC, this come negative, and when it's come negative, automatically what comes? VC becomes negative. The VCB is what? VCE minus VBE. And if VC is 1 minus 90, VB is 0.7, this is almost 189.3 volt. VCB become negative. N to N is negative. This drop become negative. So this junction become already forward bias. So forward bias is saturation region. This way you also check. Okay. So basically you have to check these two junction, forward bias. Okay. But because we are applying 10 volts, so VC cannot come this minus 90. Na? That's first thing is there. Okay. So
Sir,
now, yes, tell me.
sir, in the operating point here, 0 is the value of VCE.
VC, and this is the value of
And
IC.
this
Value of IC.
I. Okay, sir.
So IC here. So this is a maximum value of IC. Okay. This is VCE, and this is IC. In this case, this is equal to saturation. Okay. And here also you can check VC becoming negative. That is N to N become forward bias. So I told you many ways. Okay, how to check. So best check is you see only IC saturation. That is sufficient. That will automatically take care of everything. Okay. Now one more question. Same. Say this is 5 volt, and I'm keeping this 10 kilo ohm, and this is also 10 volt, and just value is say this is 1 kilo ohm, and beta is 10. Okay. Tell me what is the operation region. Find the operation region. Find the operation region. So again, you have to find first IB. Okay. So IB. So IB means what? IB is how much? Is 5 minus 0.7 upon this 10 kilo ohm. Okay, this 4.3 10 to the power 3. That means 0.43 milliampere. Okay, and IC will be what? Beta IB. That is 10 into 0.43 milliampere. That is 4.3 milliampere. Okay.
Active region resistance.
IC saturation. IC saturation is
10.1.
always remember only you have to put VC is 0. But here since this is ground, so nothing is changing. So we are just writing VCC upon RC. But if here some resistance may be there, then the
So,
equation will become different. Okay.
yes,
Only you
yes.
have to put VC 0. Okay. VC 0. So I'm writing here once more. Okay. The load line, this is called load line equation. VCE equal to VCC minus ICRC. This is the load line equation, DC load line equation. Load line equation. Okay. And for saturation, put VC equals to 0. Only VC. Equation can be anything. Here maybe many more terms we'll see later. But always you have to put VC 0. Okay. So now this will come 10 upon 1 kilo ohm. That is 10 milliampere. Okay. Which is greater than your IC value. Okay. So automatically the operation reason is active. Okay. And further confirm by calculating the value of VCE. VCE will be VCC 10 minus this one ICRC. IC is 4.3 milliampere and your 1 kilo ohm. Okay. So this 10 minus 4.3, 5.7 volt. VC is 5.7 volt. Okay. Somewhere here. So it shows the operation is active. Current is not 0. Okay. IC is not 0. Your IC is not in microampere. So operation region is here, almost middle. Okay. Sometime operation region can be close to saturation region. Sometime it can be close to cutoff region. Sometime this may be the case. Okay. That also you have to check. So either it will be active region, either it will be saturation region, either it will be cutoff region. It can be active region but near to saturation region. At the boundary it can be active region but near to the cutoff region, boundary of cutoff region. So if point is somewhere, if point is near to this point means VCC IC becomes 0 here. All point is here. That means this is the near cutoff region. It is active but near here cutoff region. If inside this one, cutoff. If here near far from saturation but somewhere here, then it is near to saturation region. Okay. So we'll solve the questions that time you understand. So operating point for this question was how much? 5.7 and 4.3. Okay. Operating point generally we write by Q cent point, not P. Now, once you understand how to find the operation region, okay. Now, next challenge is that we have seen in the transistor here, na? So, if I want to transistor to work, okay, at least I need to apply 2 batteries. Okay, I want to give 2 biasing. One is one for input, one for output. Okay, for 2 junctions. Now, if you have a practical circuits where you have a thousands of transistor on one chip, okay, or maybe more number, lakhs of numbers, okay, then how you will do? Because you cannot apply 2 batteries to each transistor. आपका जो motherboard होता है या कोई chip होता है, you have a chip only है, there is only one battery ना, you're not applying so many batteries. So batteries are basically very costly. Okay, you cannot apply each transistor you cannot give separate batteries. Okay, and if because it's costly, maintenance is difficult. So how to achieve this one? For this one, we use different kind of biasing circuits. Okay, so first question is, what is biasing and why biasing is required? Okay, why why do why do we require biasing circuits? Okay, so biasing circuits is what? Because without applying biasing, you cannot fix the operating point. Okay, so biasing is required, number one, to fix the operation region, fix the operating point or operation region. Because if you want to amplify, you need to put the point in the active region, and without applying biasing, you cannot do this one. Okay, so this is the first requirement to fix the operating point. But if you're applying two say two batteries, okay, that will make sure that everything is fixed, your operating point is fixed. Okay, but there are some experimental factors also, like temperature. If temperature increases, so what will happen? Your beta. So if your temperature increases, say temperatures go down, increase, or say T, if T goes up, what will happen? Beta is temperature dependent quantity. Beta will increase. So beta is increasing, all automatically your IC will also increase in the circuit. Okay, everything is fixed, but still you are changing the temperature of the circuit. Okay, you design the circuit for 25 degrees centigrade. Summer temperature is 40 degree, 45 degree. Okay, there are many things are happening in the circuit, so heat is getting produced, so temperature is very high of the chip. So then temperature is very high, automatically beta will raise because it's a temperature dependent quantity. Okay, so this increases, this will increase. So now when IC changes, that means your operating point is not fixed. Nah? You want to keep somewhere here. You want to keep it here. You applied biasing in such a way that this point should be here. But because of experimental factor, temperature factor, this IC may increase and it may go to the saturation region. Slowly IC may go increase, and it can shift here, and then it can shift here. So the transition may go in saturation. Okay, or sometime if IC decreasing some way, it may go to in cutoff region also. Okay, so biasing is required. There's a many purpose. So the first aspect is commercial aspect. You cannot apply two batteries to each transistor, because that will increase the cost, and maintenance battery is very high cost. Okay, so that is the commercial aspect. Other is the requirement for the circuit, fundamental requirement of the circuit to work it properly, that you want to fix. So you have to apply bias you need to apply two biasing, and then you have to fix the operating point. Okay, so the second point will be to fix the operating point and to stabilize the operating point. Stabilization of operating point. You want to stabilize the operating point. It should not, even if it's drifting, but somehow circuit should control that it should not go very far away. Either it should be independent of temperature. Your biasing should be such that your IC become independent of temperature. That means IC should be independent of beta. Okay, so my purpose is stabilization. How you can achieve stabilization? Making IC independent of beta, Okay, so biasing should be such that my IC become independent of beta. That is a good biasing. So temperature increasing, beta increasing, IC increasing, temperature increasing, reverse saturation current, ICO increasing, that will also increase IC, because reverse saturation current also gets added in this current. Okay, so that is also effect. If temperature increasing, your cutoff voltage VBE decreases. Okay, now that means you can get same IB at lesser voltage. That means now you're getting, if your temperature increases, this become low. Okay, suppose you have applied 0.8 volt. This is your powered circuit. You are getting IB versus VBE. Okay, and suppose this is the requirement 0.7, or say requirement is 0.6, you applied 0.7, so you are getting this current. Now because of increase of temperature, you require less voltage, 0.6, you require 0.6. Okay, so this 0.7 will give you high current, IB will increase, so automatically that will also increase your IC. So these are three factors which are temperature dependent: beta, IC, VBE. Okay, and because of these three factors, your IC will change and our operating point will shift. So we want to stabilize this thing. These are two important points. And of course, there is a commercial point. And third point is your batteries are very costly, so you cannot apply so many batteries. Where batteries are costly. Batteries are costly, and then maintenance of battery is difficult. There's so many other factors are there. Maintenance of batteries is difficult. Okay, so all this, for these reasons, we require a perfect or proper biasing. Okay, so now we'll go different kind of biasing and see which is biasing is perfect for our operation. So let me erase this one. So put the number one biasing, fixed biasing. Fixed biasing or fixed bias circuit. Fixed biased circuits. So this is a very elementary circuit. Okay, it is not commercially used. This is an elementary circuit, elementary biasing. Okay, so now I have a transistor. ये transistor मेरा. I am only using single battery. Okay, with single battery I am applying to bias to this transistor. Means this, using this single battery, I can connect this with single battery. I can connect a 2 transistor, 3, 4, and n number of transistor I can connect with single battery, and this single battery will provide the biasing to every circuit, every transistor. Okay, so this is my, say, plus VCC. Okay, so this is my RC, and here a circuit coming RB, and this is coming here RB, and say this is grounded. So this is my ammeter. Okay, this is my base, and say this is my collector. Okay, now current is IC. So the current which goes in the collector is called IC. Always remember. So this is IC is flowing here. No other thing. So this is IC. This is IC, and here the current which goes in the base is called base current, IB. So this is IB. This is IB. Nothing else is there. So this is your IB. Okay, and IB is going here, and here again you have VB. Okay, so tell me what is the value of IB, how to solve this one. So circuit value, beta is given for this transistor. Okay, so let me now find what is your IB. So for this kind of circuits, so this circuit is giving forward bias to this one, because this is a positive is connected to positive, NPN. So this is giving to, with respect to ground, it's giving positive voltage to this bias, and this is N, and N, so VCE is your reverse bias. Reverse bias means here This is NPN. So N it is giving plus. So this junction become reverse bias, and this junction become forward bias. That you have to take. You have to see. So because VC positive, that means VCB positive, VB positive. This VC. Okay. So now IB will be what? IB. So you can write. You can first. This is the first loop, and this is the second loop. So transistor circuits are very easy. Easy to whatever circuits so far we have done. These circuits are very easy. Okay, you only have to apply KVL in the circuit. Sometime only you require to apply nodal analysis. Okay, so this is your VCC. So minus VCC plus IBRB plus VBE equals to 0, and your IB become VCC. This minus VBE upon RB. So once you know the IB, automatically you can find what is IC by beta IB. Okay, and you have to compare this with IC saturation in the circuit. Okay, IC saturation is VCC upon RC. And once you decide what is the actual current, this and this, then you can find the VC equal to IC, RC, VCC minus ICRC, the same equations. You can find the operation region, you can find the operating region for this circuit. Okay, but this is the very elementary circuit. Elementary circuit in the sense, here you can see ICs depends on beta. Okay, so this circuit commercial aspect is good. Okay, that is, you take a one source and you connect this source with million of transistors. Like I'm here, same I can put one more transistor. I can connect the circuit. I can give the current to every biasing to every transistor. But in fundamental point of view, operation point of view, IC is dependent on beta. So this is not practically used. But just for exam point of view, question में कोई भी biasing कर सकता है. So IC is dependent on beta. Okay, so that's the thing. So I'm giving you one problem on this biasing. So you have been given RB value. RB value is 270 kilo ohm. Okay, RC value 2.2 kilo ohm. Okay, beta you can take 50, and VBE you can take 0.7 volt. Okay, and find the operation region. Let me the operation region for this circuit.
So VCC.
VCC is 9 volt. Just 1 minute. 9 volt. VCC is 9 volt. Calculate.
So what we have to find?
Operation point here. Operation region.
Okay, sir.
So for this given circuit, you have to find VC, and please find VC also. VC means here. What is the voltage here? You have to find VC and you have to find VCE. Both you have to find and tell me what is the value. And you can also find what is the value of VB. That is extra job we are doing because it will help us further. Okay, so you have to find VC, you have to also find VB. So let us find IB. IB is what? VCC. This 9 minus 0.7 divided by 270 kilo ohm. Okay, tell me how much is coming.
30 microampere.
30 microampere. Okay, IC become how much?
1.5 milliampere.
Beta IB, that is 50 into 30 microampere. Okay, that has become 1.5 milliampere. Okay, then what is the value of VCE? So first you have to find IC saturation. IC saturation is VCC 9 volt divided by RC value is how much? 2.2 kilo ohm.
2.2 kilo.
2.2 kilo ohm. Yes, sir.
कितना आ रहा है फिर बताओ?
4.09 milliampere.
4.09 milliampere. Okay, so my IC is less than IC saturation. So this is my value. Okay, and operation reason is active. Okay, and now I can calculate my VCE. VCE will be VCC 9 minus IC value is 1.5, which is lesser. That value you have to take. And RC is 2.2 kilo ohm. This cancels out. 9 minus, tell me how much is coming.
5.7.
कितना?
5.7.
5.
5.7.
Very good. 5.7 volt. Okay, so my operating point Q becomes 5.7 volt and 1.5 milliampere. Okay, and 5.7 volt itself shows you that total is 9. So if you see this graph again, this is my line, load line. This point is what? 0 VCC. This point is VCC and current is 0. This point is what? Voltage is 0 and current is IC saturation. Okay, so this is a 9 volt and I'm getting what? 5.7 volt somewhere here. This is the active region. These are the end point. VCC 0, 0 IC saturation. Okay, so by seeing the value also you can decide whether it is a middle, whether it is, if it is close to 0, then it is then near to saturation. If it is close to 9, if some point VCC comes somewhere here, then it is close to cutoff. And if IB 0, then it is surely cutoff. If IC is greater than IC saturation, it is surely in the saturation. Okay, so exactly in the saturation region. So this is operating point. Now tell me, what is the value of VC and VB? What is the value of VC? How can I find value of VC? Tell me. VC is this point. I
सर
want to. हाँ
VCC वो KVL लगा देंगे V इज इक्वल टू आई आर वाली.
हाँ, अरे भाई, दिस इज टोटल वोल्टेज 9 में से कितना लॉस हुआ? VC, अगर मुझे VC चाहिए तो मेरा VCC माइनस ICRC, यही तो आएगा. अब आप बोलोगे ये तो VC तो है, तो VC सेम ही तो है इस
Yes,
क्वेश्चन
sir.
में. इन दिस
Yes, sir.
क्वेश्चन VC इज व्हाट? VC minus VE.
V is 0 है ना?
V is grounded.
Yes, sir.
V is grounded. So here in this question, if there is no resistance, so your VCE and VCE, this point, okay, and this point and this point, this voltage is same. VC is equal to VCE. So same voltage. This is the VC value for this given circuit. And what about IB, VB?
VB minus V.
VCC minus VB is what? VCC minus IBRB. VCC is how much? 9. IBRB is how much? Tell me. 270, 30 microampere. And RB is 270 kilo ohm. How much is coming? VB. How much is coming?
तो 0.9 आ रहा है.
Hmm?
0.9 आ रहा है.
Okay, sure.
Yes sir.
0.9 volt. Okay, which is greater than 0.7 volt. 0.9 आ रहा है, 0.7 ही आ रहा है.
सर 0.9 आ रहा है. मैं फिर से निकाल चेक करता हूँ.
हाँ, ठीक है, जो भी है. चलो ठीक है. So now this VB is coming positive. VB positive means this is the forward bias. Okay. Now VBE is what? VBE is basically your VB minus VE. Okay. VB is your VB minus VE. Here V is 0. But if it's not coming same, that meaning is you are applying more than cutoff. So drop will be always 0.7. Whether you apply higher voltage also, because this is the characteristics of your diode. Huh? Actually, it is VB. You're getting 0.9, but we'll take it to 0.7 because it is the characteristics like this. This is a varying here. Okay, slightly varying here to here, slightly varying, but we always take constant value VBE. So, but we have to make sure that it should be greater than 0.7, equal to greater than 0.7. Then only it is forward bias. Okay, otherwise it becomes cut off. Or you can directly check the value of IB. If IB is very less, okay, then it's for 8, 9. Then you can say the operation region will go to cut off.
Yes.
Yes, tell me.
तो आपने यहाँ पे क्या बताया? BB minus BE ने यहाँ पे क्या
VB
बताया?
क्या होता है? VB minus VE होता है.
वो ठीक है. उसके आगे क्या बताया अभी
तो
आपने?
अभी V 0 है, तो हमारा
हाँ.
VB बराबर VB आना चाहिए.
Yes yes.
पर अभी थोड़ा ज्यादा आ रहा है.
ज़्यादा आ रहा है.
बट उसका मतलब क्या है? Here the requirement is 0.7 to start,
Yes sir.
but you are applying more than that one. Okay. So but here drop will be only 0.0 like in your diode na. Suppose your
Drop
diode,
0.7 ही होगा, है ना?
you even you apply 5 volt, here it will come 0.7 only na.
Yes yes sir.
Same way here, whatever voltage here drop will 0.7, but you have to make sure that this should be greater than this drop, then only it will start.
Yes yes. Thank you very much. Perfect.
So I'm giving now one homework. So the same for fixed bias circuit you have to use. I'm giving you RB equals to 100 kilo ohm. Okay. RC equal to 1 kilo ohm. Beta is equal to 150. Okay. And VBE, you can take 0 volt, and VCC is your 10 volt is the first case. Okay. You have to find the operation region. Okay. Operation region. So this is 100. Okay. This is question number 1. For question number 2, RB value is 300 kilo ohm. Okay. RC value is 2 kilo ohm. VCC is your 9 volt. Okay. And beta 1 is 50. So first you take beta 1, and second case you take beta 2 is equal to 150. Okay. VB you can take 0. VB both the case you can take 0. Okay. You find the ratio of IC1 by IC2. First you take beta 1 and find IC1, and you take beta 2 and find IC2 for given circuit and find the ratio. You will surely see that if beta increases, your current will also increases. So say IC2 upon IC1, you find the ratio of IC2 by IC1. So beta increases, your current is increasing, and this circuit is not doing nothing to stop this one. Okay. So this is the elementary biasing. So we'll meet tomorrow. Is the time is there for me? Was okay, it's finished.
Yes, sir.
Okay. So we'll stop here. Thank you.
Thank you sir.
Thank you, sir.
Thank you, sir. Thank you, sir.